Does anyone have any particular questions they'd like to ask? Okay, so we got one no and two no responses, so I'll just assume you are answering no. So we're going to talk about the lab today, the mass spectrometry lab. So before we talk about the lab itself, I want to talk a little bit about mass spectrometry. So this is from your book, and I want to explain a cartoon drawn in your book. So here's the cartoon. I'm going to zoom in on it. And this is a cartoon of a mass spectrometer. So let's look over the pieces of the mass spectrometer. You can see that we've got the vaporization area, the ionization area, the acceleration area, deflection, and so forth and so on. So let's talk about what happens in each of these areas. So in the vaporization area, what happens is that substances are turned into gases. So we're going to be looking at, in this particular case, they're looking at neon, which is going to be a gas. So these are individual atoms of neon floating around in the air, as it were. Now, a neon atom is neutral, and we could write that there to say that, oops, you can't see that. Neon atoms are neutral, and you could write a 0 there to indicate that it has no charge on it. Well, we don't normally do that. We just leave the 0 off, and it's assumed that it has no charge. Now, a neon atom has a nucleus surrounded by an electron cloud. So the electron cloud is where you find electrons. The nucleus has protons and neutrons in it, and both of those are called nucleons. So I like this name, nucleons. Nucleons are found in the nucleus. And these are protons and neutrons. The symbol for a proton is P with a plus sign. Neutron is N with a 0. And the symbol for an electron is E with a negative sign. Okay, if we look at one particular neon atom, so we're going to look at this neon atom right here. And we need to understand what all of these things mean. What does Ne mean? Well, it means neon. What does 20 mean? Well, that's called the mass number. And it's equal to the number of nucleons. Let's see. I can't tell if you can read that, so take a moment and move the. Okay, so you can't see that. So I'm going to put is equal to the number of nucleons. Like that. This is called the atomic number, and it's equal to the number of protons. Okay, so I'm going to zoom out. And so for this particular neon, we've got 10 protons, 10 neutrons, so 20 nucleons total, and we're going to have 10 electrons because the atom is neutral. Charges are additive. Negative charges count as -1. Positive charges count as +1. And if you have 10 protons, that's a positive 10 charge. 10 electrons is a negative 10 charge. Add it all together, you get 0 charge. So this is a neutral neon atom. And it is called neon 20. Now there's another neon atom that looks like this. Same size, 10 protons, because all neon atoms have 10 protons, all of them. If there's a different number of protons, it's not neon. And you've got 11 neutrons, and you've got 10 electrons. These are supposed to be the same size. This one is called neon 21. And you'd put another way to write it is neon 21 and 10. So the number at the bottom is always the number of protons. There's a third neon that has 10 protons and 12 neutrons and 10 electrons. So this again is neutral, and it is neon 22, which can be written as follows. So these guys are isotopes of neon. So they're variations of the neon atom, 3 different types. Any questions there about the idea of isotopes? Okay. Well, so this is kind of interesting that it has 3 isotopes, and you might venture to guess that, okay, if there's 3 isotopes, then maybe we have 33% of these, 33% of these, and 33% of these. So what is the mass of your average neon atom? Well, it's very interesting. This is the number of nucleons, and it just turns out that each nucleon weighs 1.00 AMU if you round off. I'm going to slow that down again. Each nucleon weighs 1.00 AMU. So how much does this guy weigh if it's got 10 nucleons? Well, the obvious question is, well, what about the electrons? The electrons weigh, for all practical purposes, nothing compared to a proton or a neutron. So this guy weighs 20.0 AMU, 3 zig figs. This guy weighs 21.0 AMU, and this guy weighs 22.0 AMU. The mass number, which is the number of nucleons, can also be used for the mass number, and that's why it's called mass number. Otherwise, we'd call it nucleon number. So because the mass is very close to the number of nucleons, we call it mass number. Okay, so if we have 33% here, 33% and 33% here, and averaged it, then the mass of your average neon would be 21.0 AMU. But in fact, when you look at neon on the periodic table, this is what you see, 20.1797. 20.1797. So that number at top is the atomic number. And this is called the atomic weight, which is the mass of your average neon atom, which doesn't exist. Okay, so clearly this is more than a neon 20. It's less than a neon 21, and it's less than a neon 22. Because this value is so close to 20, that means there's probably a lot more 20s than there are 21s or 22s. How would we actually determine how many of each of these and what the actual mass is? And the answer is you would use this mass spectrometer. So a little bit of background there. Now let's take a look at the mass spectrometer. And I'm going to zoom in just a little bit. Okay, so we're looking at this vaporization section. So our neon isotopes are turned into gas molecules. It's not hard to do because they're gas molecules at room temp. Let's look at this ionization area where you've got this electron gun. So I've got this neon atom, and I'll look at 20 here. And remember, it's got 10 protons, 10 neutrons, and 10 electrons. And you've got something called an electron gun, which shoots electrons at this guy. So I'm going to draw this a little bit differently. 10 protons, 10 neutrons, that's your nucleus. Here we've got 9 electrons plus 1 more electron for 10 total. And you can't see any of what I'm drawing. So here's my drawing. 10 protons, 10 neutrons, and 10 electrons. And I have written 9 here and 1 here. The electron gun actually shoots electrons at the atom. And if this electron hits another electron, both of these go to a trap. So what happens to this guy? Well, it's still got 10 protons and it's still got 10 neutrons, but now it only has 9 electrons. And so overall, the charge is -9 due to the electrons and +10 due to the protons, which means overall, this thing has a +1 charge. If you have more protons, you're going to have a plus charge. If you have more electrons, you're going to have a negative charge. So the way this would be represented is neon 21, or excuse me, 20, and this would be neon 20. And to indicate that this has a +1 charge, you write plus next to it. This is called an ion. Positively charged ions are called cations. Negatively charged ions are called anions. So this electron gun right here makes cations. Now, let's look at this mass spectrometer some more. I'm going to zoom in again. Okay, so now we have right here a cation with a positive charge. You see this repeller plate? It has a positive charge. Like charges repel, so that cation will be forced to go to the right. These are called accelerating plates, and this is the acceleration section. These accelerating plates have a negative charge. Well, opposite charges attract, so that cation with a positive charge is attracted to these accelerating plates. It is possible that that cation will hit an accelerating plate and it'll become neutralized. That means it gets an electron, becomes neutral, and it bounces off. But it might miss all the accelerating places, go right through that hole, and then here it reaches this magnet. Now, whenever something is flying straight, it stays flying straight unless gravity acts on it or some force acts on it. These guys are traveling at such a speed that in this short amount of space, gravity's not going to do a thing. So the magnet is used to change the path of the cation. This magnet can be tuned, meaning the amount of magnetism can be changed so that a particular cation, like this number 20, can have its flight path changed so that it hits the wall of the container here, hits the wall of the container up here, or goes straight through to the detector. And then you can change the tuning of the magnet so those with a mass of 21 go through. Then you can change the tuning of the magnet so that those with 22 go through and hit the detector. So you can adjust the magnet so only particular masses get to the detector. And you can count how many get to the detector. So this is how we figure out the mass of each isotope, because we tune the magnet for a particular mass. If things hit the detector, we know they have that mass. To get the relative proportions, you leave the magnet on for each different mass for the same amount of time. So like leave it on for 1 second for each of these. And the number of hits tells you how many of that particular isotope you have. So in this case, we get this sort of output. You can see that those with a mass to charge ratio of 20, so this M means mass, this Z is the charge. The charge on all of these is +1. So in this particular case, there's a lot more 20s than there are 21s, and there's about twice as many 22s as there are 21s. These are the relative percentages of the isotopes, and they are not 33%, 33%, and 33%. So what do we get from the mass spectrometer? We get a couple of things. We find out the mass of each isotope and its relative percent abundance. Okay, so that's a quick introduction to mass spectrometry. All right, now let's take a look at the lab. So I'm going to my browser, and now I'm going to open up the, I don't want the inbox. I want a shell so that we can look at the lab. Whoops. So mass spectrometry. So you'll notice here it says this lab is a little different than a lab that uses glassware, like your density lab or measurements lab. You're going to write up an introduction that includes a brief description of mass spectrometry, how it works, and the information it can provide, which we've just gone through. So right now you should get out your lab notebook and you should start writing this lab. And the first thing you want to write at the top is mass spectrometry. This is how it's spelled. Put the title in. Once you're done that, write down introduction and leave yourself half a page to fill that in. Because I'm not going to give you enough time to actually fill out your introduction while we're talking. But I do want you to write stuff in your lab notebook as this lab is described. You'll notice here it says you have a safety section, then a procedure, data, calculations, hypothesis, accepted results section, followed by follow the instructions carefully, and then you have a discussion. So in this one, you're not really going to do procedure followed by data, followed by calculations, then followed by results. It's going to be a little different. And you'll see what I mean in a little bit. You're going to submit photos. Submit photos of each section of the procedure as it is written in the lab notebook. Include your hypothesis before you test it. So we're going to practice testing hypotheses today. And I expect to see a blank space after your hypothesis because it's the last thing you put in your lab notebook. There are no additional questions, as your hypotheses, that should be plural, are the answers to the questions. Here's another place you can go to read about mass spectrometry. Here's some goals. Here's some more background. This is a tool we're going to use. I call it a mass spectrum simulator. And this is what it looks like when we go to that page. Okay, so hopefully you skipped half a page so that you can write the introduction. Maybe you skipped the whole page, that's fine. Go ahead and write your safety section. You can see the safety is, there are no safety issues with this lab. So go ahead and write that. When you're done, give me a little thumbs up or a yes. Give me some sort of signal that you've written your safety section. What's neat about this lab is you're going to get most of it written up now and not have to come back and do it later. Okay, we got a couple people that gave me their thumbs up, so we're going to move on. Step 1, do each of the following step by step. Do not look ahead. So step 1 is go to webelements.com and link to bromine. I'm going to go through a few of the directions here. Link to bromine, find the bromine isotopes, link to more isotope and NMR data, copy down the table of isotopes, copy the plot, and carefully label the axes. So let's do that part here. And this is something that you can do in your lab notebook right now. I'm going to do it with you and show you what you're going to write. So here's webelements.com. And here's the link to bromine. And if we scroll down, you see we have bromine description, physical properties. And if we keep scrolling, you'll notice we get to a place where we actually see something that says bromine isotopes and the bromine isotope pattern. And then we have more isotope and NMR data. So we want to link there. And here is what you want to put in your lab notebook. So what I'm going to do is I'm going to show you precisely what I want you to put in your lab notebook for this particular part of step 1. So are you ready for this information, people? So let's put this in our lab notebook. I mean, no better time than the present. So I'm going to go back to the lab mass spectrometry, go to Web Elements, blah, 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 blah. Copy down the table of isotopes, symbol, mass rounded to the ones, and natural abundance. So I'm going to go back to Web Elements. So if I make a list of this information, it's all right here at the top. So I ask you to round the mass to the ones. What does 78.9 become when you round it to the ones? Answer, becomes 79. What does 80.91 round to? Becomes 81. So here's what your table is going to look like. I'm going to do a change view or new share. So here's what your bromine table is going to look like. So this is your Web Elements bromine data table. You're going to write the isotope. So one of the isotopes is bromine 79. The other one is bromine 81. You'll notice we don't write the 35 at the bottom because you can always figure out it has 35 protons by looking at a periodic table. There's bromine. It's got a 35 at the top. So that's what you would write here. It's kind of unfortunate, I guess, that this number at the top on the table is what you write on the bottom over here, but that's the way it is. When we look at the mass in atomic mass units, bromine 79 is 79.0, 81, oops, 81 is 81. We don't need that 0 because I said round to the ones. And the percent abundance or natural abundance, we've got a 50.69%, I believe. Let me double check that. I can double check that without a, hang on a second. Now I just made it all go wonky. Okay, that's better. Okay, so the percent abundances or natural abundance is 50.69 and 49.31. Okay, so that's your data table. And then you want to draw the graph. And in this case, we don't need to draw a really big graph. So I'm just going to do this. This is the mass to charge ratio. This is 79. This is 81. You'll notice that our x-axis does not start at 0, because if it did, from 0 to 79 would be empty. This we're going to call intensity. On Webb Elements, they call it the relative intensity percent. We're just going to call it intensity. And this is the natural abundance in percent. The 79 for intensity is at 100. And the 81 for intensity is at 97.28. Okay, so this is 100 and this is 97.28. And I'm going to cross this out and I'm going to write 100. And then below this, I'm going to write 50.69 because that's the percentage here. And I'm going to write 97.28 and then 49.31%. And this is what our Webb Elements site shows for the plot. And you see these little mistakes I made here? I'm not going to erase them because it's in my lab notebook and you're not supposed to erase anything. So this is what I would expect if you made mistakes. You just cross them out. That's all there is to it. Any questions for the table or the plot that you're supposed to put in here? Now's the time to ask. Okay, let's go back to the lab now. I'm going to switch my share back to my browser. And I'm going to go to the lab. So we've just copied these things down. Do you see this thing that says the peaks are signals from the mass spectrometer? The lines on the spectrum at 79 and 81 are called peaks. They're also called signals. So those are used interchangeably. It's a signal, it's a peak. Read the caption below the plot carefully. So let's take a look at the caption below the plot. So I'm going to go to Webb Elements. Isotope abundances of bromine in the above. The most intense ion is set to 100%. I call it 100 intensity, since this corresponds to the best output from a mass spectrometer. The best means the tallest peak. This is not to be confused with the relative percentage isotope abundances, which equals 100% for all naturally occurring isotopes. So if we look above, the red numbers are the intensities, and that matches the red y-axis. And the blue numbers are the percentages, which matches the blue y-axis on the right. Notice that the percentages of 50.69 and 49.31 add up to 100%. Notice that the intensities 100 and 97.28 do not add up to 100. So that's how a mass spectrometer works. You actually get the red data where they say the tallest peak is 100 and the shorter peaks are measured relative to the tallest peak. Now, it's not like the tallest peak means that you got 100 isotopes that hit the detector. It probably means more like you got 5 million hit the detector. But they say, okay, we're going to call that 100. And for the 81, how many hit the detector? Well, probably 4,800,000 or something like that. And so we don't want to write those numbers at the top. So we normalize those so that 100 is the biggest and 97.28 is the smaller one for bromine. So how do we figure out those percentages of 50.69 and 49.31? That I'm going to show you now. So Can everyone see my hand? Can anyone see my hand? Okay, I must not have hit the share correctly. Can anyone see my hand? Okay, so what I'm going to do is show you this. This is intensity. This is mass to charge. We've got a 79 and an 81. The 79 is 100, and the 81 is 97.28. We want to show how this can become, sorry about that, I'm zoomed in for some reason or other. We want to show how this can become the following. Okay, are you ready to see how what is on the left, which is what the mass spectrometer reports, turns into what is on the right? You ready to see that? Okay, so I'm going to move this up a little bit. And here's how you calculate percentage. Percentage is equal to part over whole times 100%. That's how you calculate percentage. So if you have 5 brown eggs out of 10 eggs total, that's the whole. 5 over 10 times 100% would be 50%. That's how that works. In this case, the percentage for bromine 79 is going to equal the intensity of bromine 79 over the intensities of bromine 79 plus bromine 81, all of this times 100%. So that's the part we're interested, bromine 79. The whole is both intensities, part whole, and then 100%. So if I actually plug numbers into here, I get 100 over 100 plus 97.28 times 100%. Now this becomes 100 over 197.28 times 100%. Both 100s are exact. So we get 5 zig figs out of this, and we actually get 50.689%. And if you take a look at that number compared to that number, they're really darn close. They didn't round properly. So this is one of those calculations you want to put into your book where I said you're going to have like a procedure, et cetera, et cetera. The procedure here would be go to Web Elements and get the data table and the mass spectrum. Okay, any questions here about how we calculate that 50.689 and how it matches there? Any questions about that? Okay, so let's do this. Let's do the percentage for bromine 81. What number am I going to put up top? The intensity of 79 or the intensity of 81? The intensity of 81. What am I going to put on the bottom? The sum of these two numbers, which is 197.28, and then times 100%. In this case, we only get 4 significant figures because 97.28 has 4 zig figs, even though 197.28 has 5. I'll say that a little more slowly. 97.28 has 4 significant figures, 197.28 has 5. 100 has an infinite number of significant figures, so we get 4 zig figs. So do your calculations. When you get an answer, give me a thumbs up. Okay, we got a couple thumbs up, and you get 49.31%, just like above. So this shows you how we take intensities and turn them into percentages. Okay, now I'm going to go back to the lab. So I'm going back to my web browser, and I'm going to go to the lab write-up or the lab description. So do you see this part here where it says the intensities are converted to percentages as follows? That's what we just did. Okay, now we're ready for the next part. What we want to do is we want to take a look at the mass spectrum simulator just to see what it does. And to link to the mass spectrum simulator, it's towards the beginning of the lab. And that is the link right there. https www.sysweb, etc. So if I link to that, you're going to see a site pop up that looks like this. So we're told to type BR into the chemical formula. The chemical formula is here at the top. Well, not at the top, but here in this window. And I'm going to type bromine, uppercase B, lowercase r, and hit enter. Now, do you see the data table? This first column of numbers are the masses. The second column are the intensities. And if we look at the plot below, you can see that we have 2 signals, one at 79 and one at 81. And we've got 197.5. And that sounds really close to the numbers we had before. Let's take a look at what we're instructed to do. We're instructed to report the data table, draw the spectrum, and calculate percentages. So I'm going to go ahead and switch my view so you can see what the table looks like. And then we'll draw the spectrum, and then we'll calculate percentages. Okay, so when you go to that simulator, here's what the table looks like for bromine. You have 2 isotopes. One has a mass of 79. The other has a mass of 81, and that's straight from the simulator. The intensity is 197.5. This isotope here is bromine with a mass number of 79, and this one is bromine with a mass number of 81. See, the mass number equals the number at the top when you write the isotope, when you round to the ones. So here's the table. So this one is given a 100. And this one is given a 97.5. Now you'll notice I did not take out a ruler to make that 97.5 compared to that 100 exactly. I just know that 97.5 is really close to 100, so I made this other peak almost as tall as the 100. Are there any questions about that? You're not supposed to measure it. Okay, we want to take this table and turn it into something that looks, or not table, we want to take this graph and turn it into something like this, where you still have a tall peak and a shorter peak, but we want the percentage here and the percentage here. So we want percentages. So how do we calculate percentage? Part over whole times 100%. So for this bromine 79, what's the part? 100. What's the whole? 100 plus 97.5. So you're going to get here 50, you actually get 4 significant figures. So you get 50 point, I'm not sure. I'm gonna have to do the work. You get 50.6%. I'm sorry, 50.63%, 4 significant figures because of 197.5. Any questions about that percentage for bromine 79? Okay, how about bromine 81? Go ahead and calculate that percentage, and when you're done, give me a thumbs up. Okay, so we get 97.5 over 197.5 times 100%. And I believe we get 49.4%. 3 significant figures because of this 97.5. Okay, the next thing you're asked about is, I'm gonna have to switch my screen back to the web browser so that we can look at the lab. This says, comment on the calculated percentages from the simulator compared to those found on webelements.com. So I'm going to pull up my piece of paper here from Web Elements, and I'm going to go back and do my switch screen again. Okay, here's my Web Elements. Here's my simulator. So I've got 50.69% from Web Elements, and I've got 50.63% from the simulator. I got 49.31% from Web Elements, and I have 49.4% from the simulator. So what's our comment on those percentages? Are they close to one another? Are they wildly different? What do we want to say? And then after you comment on that, you want to also talk about, well, why are they a little bit different? And the answer has to do with the tables. So let's look at the tables. Do you see how with this table you have 197.5? So this is the simulator. And here with the web elements, you have 197.28. So this is where they differ. And that's why you get slightly different numbers, is because these numbers are slightly different. I mean, let's face it, if you had $97.50 versus $97.28, you would not be saying, woohoo, I'm so much richer. They're about the same. What can you buy for 22 cents these days?
Gum.
What'd you say?
Gum. Don't know.
Can you?
Gum. Actually, no, I think it's like at least a quarter.
I think it's a quarter. I don't think 22 cents will get you gum.
Or if you buy a $1 pack at the Dollar Tree, divide that by the amount of packs.
But you're going to have to pull together
Yeah.
6 people with 22 cents so you have enough for the gum and tax. No, my
True.
friend, no. I think for 22 cents, what you can get are 22 thoughts. A penny for your thought. And that's all you're going to get. Thoughts are cheap. So any questions about the similarities here and the slight difference? Let's move on to step 2 now. So far you haven't had to take a photo of anything, but now you're about to have to take a photo of your work. Step 2, there are 2 isotopes of boron. Boron 10 is the way we'd say that, and boron 11. I'm going to stop right there. Boron 10 has 10 nucleons. Boron 11 has 11 nucleons. Each nucleon weighs 1.00, so boron 10 weighs 10.0 atomic mass units. Boron 11 has 11 nucleons, each weighing 1.00, so boron 11 weighs 11.0 atomic mass units. Any questions about that? Okay, so one of them weighs 10, the other weighs 11. Now, let's say that for these 2 isotopes, in the universe, it's 50% boron 10 and 50% boron 11, equal amounts of each. What would the average boron atom weigh? Not 10 and not 11, but what? Well, with equal amounts, it should weigh right between the 2. What's right between 10 and 11? 10.5.
10.5.
Yeah. Now, what if it wasn't 50-50? What if it was 10% boron 10 and 90% boron 11? What would the average be closer to? 10 or 11? I'll say that again.
11.
Okay, you got it. Let's look at the reverse. What if there were 90% of the 10s and 10% of the 11s? What would the average be closer to?
10.1.
Be closer to the 10s, wouldn't it? Okay, so keep that in mind. Now, the atomic weight of boron is 10.1 AMU. That means your average atom weighs 10.81 AMU. Based on this information, draw a qualitative plot of the mass spectrum of boron. Remember to make the largest peak 100 and draw the other peak proportionally shorter based on your intuitive guess based on the information provided. Once you have this drawn, take a photo. There should be blank space following, so I know you haven't done the rest of the lab. Take a photo of your hypothesis, and you're going to be sending that in. All right, so right now you should be making your spectrum, your plot. I'm going to switch screens. So we've done a lot of these plots, but you haven't done one on your own yet, have you? So what do you think? How does this look for a start to the plot? You guys like that? You do, don't you? That was a yes or no. You're supposed to say, yeah, I like it. That's a good start.
Looks good.
What are we going to put at the bottom? Let's see. What did we put at the bottom of all the rest of these? M stands for mass, Z stands for charge. So what are we going to put at the bottom of this guy?
Mass over charge.
Right. And if you take a look here, intensity, intensity, right? So what are we going to put here?
Intensity.
Intensity. And we want our biggest one to be 100. What are we going to put here? Do we want to put 79 and 81? Now remember, we're doing this for boron 10 and boron 11, which has an atomic weight of 10.81 atomic mass units. What do we want to have for the masses down here? 79 and 81 or something else?
10, 11,
What's that?
10, 11.
10 and 11. Why is that?
That's what you're measuring.
How about because boron 10 has a mass to charge ratio of 10 and boron 11 has a mass to charge ratio of 11. See, this is 10 U over a charge of plus 1. This is 11 U over a charge of plus 1. So this guy's 10 and this guy's 11. So I'm trying to get you to be willing to actually say, oh, it's 10 because that's how much it weighs. And I'm trying to get you to say it with authority, not like it's 10 because I think that's how much it weighs. I want to hear oh, it's a 10 because that's how much it weighs. I want attitude. So let's hear it.
It's 10 because that's how much it weighs.
Only one of you has attitude? Is that right? Come on, we can do better than that.
It's 10 because that's what it weighs.
That's two of us. How about this one?
That's 11 because that's what it weighs.
That's right. Okay. Now, which one are we going to draw as the 100% or the 100 intensity? The 10 or the 11?
The 11?
I'm looking for an answer, not a question.
I was going to say the same thing.
That still sounds like a question.
The 11 because the atomic weight's closer or leans heavier towards 11 than 10.
Right. And that's why I had you do that thought experiment where if it's equal proportions, it should be 10.5. But if there's more 11s, it should be closer to 11. And if there's more 10s, it should be closer to 10. How can we show people and convince people that that's closer to 11? I'll show you. This is what I call a number line. There's 10, there's 11. Where's 10.8? Right there. 10.8 is closer to 11, so you got more 11s. Now, how tall are we going to draw the 10? Now, that's up to you. So go ahead and draw it. Whatever you draw is your hypothesis. And the cool part about this is if your hypothesis is wrong, it's still a hypothesis, which means it's right. A hypothesis is your educated guess that you will test. When you're done drawing the line here for the 10, give me a thumbs up. Okay, we got 2 who are done. Now, this is not supposed to be something that you have anxiety about, or there's anguish. You just draw it based on your gut feeling. Okay, take a photo of it because you're going to send it in as part of your assignment. Okay. I'm going to give you a little bit more time to take that photo. And now guess what we're going to do, people? We're going to test our hypothesis. So one common hypothesis is they say that, oh, the 10 is really short. And another hypothesis is that the 10 is actually kind of long. So here's your 2 hypotheses in general. Okay, so let's take a look at the actual results. So this is the literature value, as it were. I'm going to go to my browser. I'm going to go to Isotope Distribution Calculator, and I'm going to type in the letter B for boron. And let's see what we get. We get, hey, we get 2 peaks, one at 10 and one at 11. The one at 11 is the 100, and the one at 10 is about 24.7. Okay, so let's go back to my share where I have the drawings where I drew the 2 normal guesses that people make. Let's evaluate each of these. So we're going to evaluate. What can we say about this particular spectrum? Did we predict a peak at 10 and one at 11? Did we do that? And we did. In what we just saw, was there a peak at 10 and 11? Sure enough. So we got that right. Here we said that the 11 peak would be the 100. And what was the 11 peak in the simulator? It was 100. And here we said that the 10 peak is going to be less than half the height of 11. 10 is much smaller than 11, and it was. So check, check, check. Your hypothesis checked out on all parts. Let's evaluate this one. Did we get the 10 and the 11 on this one? You bet your bippy. Did we say that the 11 would be the 100 peak? You bet your bippy. So on both counts, we got that part right. But here, where we kind of made the mistake was that the 10 was just a little bit less than the 11, not a lot smaller. So is this hypothesis at the bottom a good hypothesis? The answer is yes. Why? It's a good hypothesis because we used some background to come up with it. We just didn't, pull it out of our butts and say, well, there's no other explanation for it, so it must be ancient space aliens. We had ideas behind this to develop this. Okay, so can this hypothesis be tested? Well, sure, we just tested it. So that's what makes this a good hypothesis. We put some thought into it, and then we could test it. Any questions about these hypotheses? So this is yes or no. Do you understand that both hypotheses are valid and can be tested? This is a yes or no. Do you realize that both hypotheses are valid and can be tested. Okay.
Yes.
And that's what I want. So this is why I'm asking you guys to draw on your hypothesis, take a picture of it, and then test it. I mean, you're becoming a real scientist when you do this. As a scientist, you have to be willing to be wrong, but also learn from your mistakes. People who are not willing to be wrong and not willing to learn from their mistakes shouldn't be scientists. Can anyone think of a person who should probably not be a scientist? You can probably think of a relative, right? Someone not willing to be wrong and not willing to learn from mistakes. Okay, that would be me and my family. Okay, let's go back to the share and let's move on to the next step. So I'm going back to the lab, and here we're looking at step 3. So I start off with that there are 7 elements where the atoms don't come in singles, they come in pairs. Those 7 elements are hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. If you look at them and you see HON, that could be pronounced HON, Cl could be Col, and BRIF could be Briff, Hunkelbriff. That's one way to remember it. I don't know how to write out Hunkelbriff as a word, so I didn't bother doing that. Another way people like to remember this, especially if they're 18, is have no fear of ice cold beer. I don't know what it is about teenagers and beer, but gets them all giddy. Oh, beer. Okay. So this is a true story, just so that we can break the ice here. When I was 18, you could actually buy beer. That's how old I am. I could go buy beer at 18. It wasn't as strong as the 21 age beer. So if you're 18 and you're buying diluted beer, what do you do? And the answer is, instead of buying 1 6-pack, you buy 2. Or in the case of me and my friends, we would just go in and each buy a case. So that diluted beer wasn't a very good idea. It's like training beer. I had training beer when I was 18. Okay. So elemental bromine is actually Br2 and not Br. Now I'm going to do a share because I want to show you what happens when this goes through a mass spectrometer. So here's a bromine atom. It goes through your electron gun and it becomes a bromine cation, and then it goes to the detector. So if this is bromine 79 and it's still bromine 79, what mass will be detected here? 79. Now, what happens if you have 2 bromines that are stuck together? It goes through your gun. You still have 2 bromines, but now it has a positive charge, and it goes to the detector. How much will this sucker weigh when it gets to the detector if it stays together? Who wants to make a guess?
$158
Why are you making that guess? I like that guess, but why 158?
because there's 2 stuck together and the mass of 1 was 79, so 79 times 2.
Excellent. So to draw out what you're describing to me specifically, you're saying that it's 2 79s And when it gets to the detector, it weighs 158.
Exactly.
Fantastic. That's what I love about this. But do you know this is going to happen, or is this your hypothesis?
Hypothesis?
Yeah, because you don't know. All you know is Tony said it's going to go through the detector, it won't come apart, and you're assuming that the masses add together and it gets you 158. That makes total sense, right? You're not going to say, well, once you take the electron away, these masses kind of confabulate and turn around, and they could either lose mass or gain mass. That doesn't make sense, right? So you say, hey, 79 and 79. Now, how many isotopes of bromine are there? There's two of them. There's not just 79s, there's 81s. So what is our mass spectrum going to look like down here? We already have a 158. What else are you going to see? So I want you to think about that. Anyone else have any ideas about what else we might see?
162.
Why is that?
81 doubled is 162.
An 81 and an 81. Fantastic. So we have a reasonable justification for our guess. You always want that in your hypothesis, not something off the wall, but something that sounds reasonable. So this would be an 81-81. Any questions there? Okay. Anything else? If nothing else, how about the intensity? Which of these is going to be bigger when we know that bromine 79 is a 100 and bromine 81 is a 97.5? Which pair will be bigger, 79-79 or 81-81?
79,
Why?
because it's closer to 100.
How about we say it a little bit differently? The odds of having a 79 are a little bit better than having an 81. That's a given.
Mm-hmm.
So therefore, having two of the more common isotopes is going to be more probable than having two of the less common isotope. Now, in this case, is it going to be wildly different?
No.
So if we make this the 100, how big is this one going to be?
Just below it.
Is this a hypothesis that can be tested?
Yes.
That's a yes or no.
Yes.
We have a mass spectrum simulator, don't we? So guess what? We can test it. Is this a valid hypothesis? A good hypothesis because we used information to get it and because we can test it? That's a yes or no.
Yes, it is.
Yeah. You're supposed to be saying, you bet your bippy. Because you bet your bippy means, heck yeah. So you should draw this in your lab notebook and then take a photo of it. And you might want to even put BR2 hypothesis. And then if you want, because you've got time, you can draw a unicorn next to it or some sort of a Gaelic drawing that people do. Very symmetrical and cool looking. Give me a thumbs up when you've done putting that in your lab notebook and taking a photo. Okay, we've got 2 of us that are done. I'm going to give 3. I'm going to give you a little more time to get that. Guess what we're going to do next? Test our hypothesis. So let's test this sucker. I'm going to change my share back to my web browser. We're going to go to the simulator. And here I'm going to type in BR2. Oh, there it is. Notice when I type in BR2, it's uppercase B, lowercase 2, R, I'm sorry. And then the number 2, there's no way to do subscripts here, so you just write them as a normal character. I'm going to hit enter. And let's see. Sure enough, there's the 158. Sure enough, there's the 162. And sure enough, the 162 is a little shorter than the 158. But what do you see here in the data table that we did not predict?
$160.
Yeah, where'd that come from? Anyone want to make a guess?
It's just the the median. I don't know.
Okay, so if it's a median, you're talking about an 80 and an 80, but there are no 80s.
Right, exactly.
So it's not an 80 and an 80 because they don't exist. I mean, that's what I expect as the first response.
An average of the 2?
No, it's not an average of the 2 because you don't really have average isotopes. It's either a 79 or an 81, period.
Is it a 79 and an 81 together?
Bingo. It's a 79 and an 81. Do you see how our hypothesis suggested that isotopes are isotopist? They don't hang out with other isotopes. We had a 79 and a 79 and an 81 with an 81, but they couldn't mix. It's kind of like a grade school dance where they don't really want to mix yet. You know what I mean? But it turns out they can. Now, I'm going to change my screen. So now we have a 160, which could be a 79 and an 81. So there's my 160. Now, 2 79s are more likely. 2 81s are less likely. What about a 79 and an 81? What would you expect that to be compared to these other 2 peaks?
It said it was at 100.
I would expect it to be taller than this one, but shorter than that, wouldn't you? Because these 2, a 79, 79 are most likely. 81 and 81 is less likely. So 79, 81 should be in between. Does that make sense? It should. But what we saw was this. The 160 was actually twice as tall as the others. So what's our explanation? Well, I'm going to do a 2-minute explanation, and you'll probably want to watch my explanation in some of those other videos from this morning. Look at the last 10 minutes or so. Here's the explanation. It has to do with something called Mendelian genetics. You guys ever heard of that? Where you have these genotypes, like maybe you have GG, GG, or GG. So this is 2 recessives, 2 dominants, dominant recessive. So this is one parent where they have a GG, and this is the other parent, they have a GG. And here you're going to look at what are the odds of what your offspring is going to get. Well, this offspring is going to get a GG uppercase. This one's going to get a G lowercase g. This one's going to get a lowercase g uppercase g. And this one's going to get a lowercase g. So these guys are going to look the same, because you can't really tell the difference between a GG and a GG when the one's uppercase, one's lowercase. So what are the odds of getting this guy? 25%, this guy 25%, this guy 25%, this guy 25%, which means your GG uppercase is 25%. Your G uppercase lowercase is 50%. And your lowercase GG is 25%. If I were to plot these, there's GG at 25, there's GG at 50, and there's GG at 25. Does that look like our spectrum?
Yeah.
It roughly looks like it, right? So the idea here is that when we take a look at the possibilities, not only do we have to think about what's pairing together, but we need to think about the order in how they're pairing together. So you could have a 79, 79. You could have a 79, 81. You could have an 81, 79, and you could have an 81, 81. And so here, that's going to weigh 158. These two will weigh 160, and these two will weigh 162. So what are the odds of getting a 79, 79? Well, it's 100 times 100 divided by 100, because 79s are 100s. What are the odds of getting a 79, 81? Well, 79s are 100. 81s are 97.5 over 100 is 97.5. What are the odds of getting an 8179? Well, it's 97.5 times 100 over 100, which is 97.5. So these are relative probabilities right here. And what is the probability of getting this 162? Well, it's 97.5 times 97.5 over 100, which we're going to call 95.1. So really, when we look at 158, we're looking at a 100. When we look at 160, we're looking at 195, because we're adding these two together. And here we're looking at 95.1. So let's plot these numbers. So if this is 195, how big am I going to draw this 100 at 158? And the answer is, that's 195. I'm going to draw this one about halfway up, but a little taller. How am I going to draw the 162? Well, 95 means not quite halfway. Does that look like the spectrum we had?
Yes.
Yeah. But how do we make this so this is 100? Because I'm going to go back and do a share to show you that that top one there, the middle one, it says 100. So let's take a look at that. So do you see that middle peak says 100? Actually, it doesn't say 100. It says 160. Oh, that's the mass. Sorry. I have to go to the numbers here. Do you see how the 160 says 100 in the table? So let me show you how to take this guy and turn it into what looks like our table. And then we're going to call it quits. So we have this 195.0, 100, and 95.1. And we want to turn this so that the middle peak says 100 and these other peaks are relative to that. So to turn this guy into 100, here's what I'm going to do. Oh, you can't see what I'm doing, can you? So this is what we have. We want to turn it into this. How do I turn 195 into 100? Here's the simple answer. I take 195.0, I divide by 195.0, and I multiply by 100, and I get 100. I know it looks like I'm cheating, but I'm not. Any questions about how I turn 195 into 100? Yes or no? Okay, what if this were 501? How would I turn that into 100? 501. How do I turn that into 100?
Divide by 501 and multiply by 100.
That's all there is to it. Now, what are the rules of algebra? Whatever you do to one thing, you have to do to the others, right?
Mm.
So if I divide this by 195 and multiply by 100, what do I have to do to this guy?
The same thing.
Divide by 195 and multiply by 100. Let's see what we get. $51.28. What do I have to do to this guy?
Same, divide by 185 and multiply by 100.
That's right. Let's see what we get. And I get 48.8. So that's 100, that's 51.28, and this is 48.8. And this is 158, 160, 162. Let's see how that compares to the simulator. So 51.28 and 48.8, and here's the simulator. 51.3, we have 51.28. Are those pretty much the same thing? You bet your bippy. How about the 48.8? Did we get 48.8? You bet your bippy. So that's how we can make this thing kind of look like what we see there. And that's how we can make the prediction. We can use this guy right here to make the prediction. Where did I put that? I don't know. I'm going to go here. Do you see here that I did something similar? Here's the GG. And you see here I did the 100 times 100 over 100. This right here above with the P's is called a Punnett square. You can see here that below I made what's called Tony's square. So there's Tony's square. And we can use that to figure out what the spectrum looks like specifically. Okay, so we're supposed to analyze our results. We might say, okay, we missed the 160 because we didn't know that they could pair with isotopes of different types. And we didn't know that the order matters for the isotopes. Okay, finally, this is actually, we've gotten into step 4. So step 4 begins with an explanation for why step 3 was a little weird. But there's the last part of step 4, which says, okay, get atomic chlorine and predict the spectrum for elemental chlorine. So we're going to use the simulator to get chlorine, and then we're going to predict Cl2. So let's use this simulator to get chlorine. So you want to write this data down. You don't need the plot, you want the data. So one chlorine isotope has a mass of 35. Its intensity is 100. The other one has a mass of 37 and its intensity is 32.4. Now I want you to listen carefully. You're supposed to come up with two plots, not one, two. One is based on this information, figure out what masses you expect, make a guess as to which peak will be the tallest, and then draw the other ones relative to the tallest peak. Use your gut instinct for which one's going to be the tallest and how tall the other ones will be. Fair enough? That's called a qualitative guess. And that's a hypothesis. You are then going to take this data and you're going to do the calculations, Tony's square, and you're going to calculate what you expect for the mass spectrum. And you're going to draw that. So your qualitative and your quantitative may not be the same. They often end up being slightly different. After you get both of those hypotheses, you're going to take a photo and then guess what you're going to do? What do we do with hypotheses?
Test them.
Test them. How are we going to test this hypothesis? You're going to go to the simulator and type in Cl2, but don't do that until you make your hypothesis, because otherwise it's like cheating. All right, so thanks for attending. I'll post this hopefully later tonight. Have fun with it. This is due Monday. And I don't mean yesterday, I mean next Monday. Fair enough? Last thing I'm going to tell you is you're going to kind of write this procedure, data, hypothesis, and the results all in one little section, step by step. And then you are going to write a discussion for everything. So what are the things that you think might go in the discussion? Let's help
Our
each other out.
hypothesis, and how we
Well, here's what I would put in
results.
my discussion. I'd say, well, we can use the mass spectrum to get the mass. Here's a data table that tells the mass right there. We can use the mass spectrum to get the intensities. The intensities can be turned into percentages, right? And then lastly, we can use the mass spectrum of an element to get the mass spectrum of two elements bonded together. And we can do that qualitatively versus quantitatively. Which one's going to take more time, the quantitative or the qualitative?
Quantitative?
Quantitative, because you have to hash the numbers out. It always takes longer to calculate things. Qualitative is what we in chemistry call the hand waving. Well, it's because of this. And you kind of get close, but you don't really get it precisely. Are you with me? So if you're looking at someone's height and you make a guess, oh, look, I see them standing in the door frame. I think they're 5'4". That's qualitative. You're not really measuring. But if you take a ruler and hold it next to them and measure them, that would be quantitative. What takes less time? Qualitative. Okay, so there are times when qualitative works and there are times when you need quantitative. Fair enough? So you probably want to have that in your discussion, that you're able to make predictions that are qualitative and quantitative. And hopefully you'll be able to say in your discussion, and you're able to do so accurately. Capiche? Now, the last thing is there's no assignment for this. All of your hypotheses and the tests are the assignment. You just have to be willing to make a hypothesis and test it. So I hope you are willing to do that and have a little fun with this. And thanks for attending. Hopefully we will see you tomorrow night. So everyone say goodbye.
Bye.
Bye.
good day.
Thank you.
Everyone, thanks for attending.